primarily, because you have possible duplicates in your database. The use would then, the whole blast report would fit in one toast page. But now we can't have referential integrity between the two sequences across that table, right? So we get a huge benefit at the expense of an integrity cost. Now, ordinarily, that's not a really good thing, right? Normally, integrity is king, and we sacrifice the speed to make sure that happens. But in this case, because of our access patterns and our database flow, this was a real one. But what do we do about those orphaned records? So what we would do when we would retrieve the rows, if we were retrieving them for display, is we'd unmess them. We would then join them against the other table and return the result. That seems like that's a really, that seems like you're going to lose all of the benefits that you get through denormalization if you do that, right? But one of the key things here is that the unmess function is planner opaque. So planner doesn't have any idea how big your array is that you're sending it, right? So it plans for, 100 rows, and it might get 1,000 out, or it might get 0 out, but it would choose a consistently good plan. And that made a big difference also. It would also mean that if we're pulling this for processing, we don't have to do that. We don't have to do that as well. We can just filter things out because, we didn't find the sequence, so underneath it. So the major trade-off, however, is space, and in particular, it's taking the name table. So now if you do a search on how many rows we have, that happens really fast, because that table has like 2 integer values for each row. It might have 150 million rows, but that's really fast. It's not getting through that many data pages. So finally, the last case that I think is worth looking at, and this is also something which comes up in Postgres, is how we handled semi-structured data. Now, one of the key things here is that we were storing these structured text documents. It could be XML, it could be JSON, it could be something else. Right? So these are structured text documents, and they come in from a variety of sources, and we store their source, and we store the text. And each source has its own format. But one of the important document types we were storing were patent documents. You publish in a very specific format called SXT. And at some point, somebody says, we need to be able to sort these patents on the order of patent dates. And we grab the patent date out of these documents? No, we hadn't, right? And this is a table with 250 million records. So what do we do? Obviously, we could write a worker and we could go through all these documents and pull out the patent dates, and we could do something like that. That's a possibility. But what we did instead was we extended SQL. And then, so what we did was we wrote a PL-Pro function, take the PL Python to be similar, and basically it takes in the database row to check to see if it is a patent application. If it's not, it returns a null. We don't want to do processing. And if it is a patent application, it returns the date. Simple. Fast. And we mark it immutable, and we index the output. Yeah, functional index. Then we build the index on, and now researchers can suddenly search on patent dates. And they can order patent results on a given protein or things like that, and they can do that fast. And instead of taking us a long time to process the data, we have that within a week. So this is some very simple sample code. And basically, this is PL-Pro, and of course, that has both the benefits of Perl of being very simple and easy to understand if you know Perl, and having the drawback of being totally opaque if you don't know Perl. And I don't think this is the specific code we use. This is something I wrote quickly as a illustration. One of the things about this is that PL-Pro doesn't allow use statements, but you can use strict and use warning. So in the event where you're using PL-Pro, you can still use strict, and I highly recommend that. But you'll see we mark it as immutable. You can return it as a text string, and then use another function to, for example, cast it as a date. Obviously, something could go wrong here. If we ever got a malformed date in some file, we get getting database errors. So this is something worth possibly being a whole lot more defensive about when you're coding than we're doing, but it was something that really helped us out. And so here's an example of where functional indexes and this sort of thing really kind of save our day. So then, just a brief bit about what I think the major takeaways are in this sort of environment. So a lot of times, as I always say, as you go up one order of magnitude in database size, typically the sorts of problems you deal with change. right? So the specific problems that you look at 10 terabytes aren't the same problems you're looking at 1 terabyte. They're not the same problems you're looking at 1 terabyte as they are at 100 gigabytes, for example. Every time you go up one of these orders of magnitude, the problems change. But there are certain things which are sort of constant across that. The first is you want to get people together who are able to look under the hood of the database and understand what's going on, because databases provide a lot of abstraction from what's going on under the hood. And when you're faced with a strange problem, those abstractions are usually actually blocking your sight of the root cause of the problem and hence what you need to do to fix it. The second thing is, when you're looking at a new feature over a reasonably large data set, very often some of these advanced features like functional indexes can really come in handy in terms of saving your day, getting a feature out much quicker than you would have thought possible, right? And the final one I want to spend a little more time talking about is simulating testing and monitoring. We tend to think about writing tests. Writing tests that can run in the database, for the job queue stuff, we wrote a bunch of benchmarks. We wrote a bunch of tests. But some of these things are very, very difficult to test. For example, the race conditions. For some of these, one of the tools that we fell back on that I didn't really talk about in the previous slides was actually trying to come up with writing some simulations. When we wrote the second version of the job queue, one of the things I spent a couple of days in was coming up with simulations of different algorithms of selecting jobs to see what would actually clear the job queues faster. And of course, those aren't like running in the database. Those were just quick Perl or Python programs that were trying to simulate the problems that I was foreseeing. And that actually helps narrow down the sorts of problems we expected to find and helps us find solutions that are much faster. I know we don't often think about trying to simulate problems, but modeling and simulating problems is actually very, very helpful. And then the final thing is monitoring. One of the key things that we found was figuring out what to monitor on a database isn't always very clear, right? We ended up monitoring some things that we didn't expect to be important. It's such things like, what's the difference in value between our current maximum allocated transaction ID and our current minimum allocated transaction ID? That turned out to be very important in looking for and containing the value problems. And that kind of gets back to this question of looking under the hood and always being willing to say, okay, yes, there's a whole bunch of abstractions, and yes, it doesn't work this way, but it does. And so if it's not working this way, let's figure out how it's working and how we're getting into the situation we've done ourselves in. And I guess the final thing I would say is that, the human aspects of getting the people together in teams to solve problems that seem beyond the capability of one person to solve is something that I found to cut the time to resolution pretty dramatically. So I think those lessons are actually quite applicable even before you get to do something on that scale. So that's the talk portion of this, and then I expect that in a few minutes we'll have pizza, and then we can kind of mix and go and have just a general sort of discussion about these thoughts. And I wanted to take over the world, of course, and that plan to take over the world was dependent on everyone beginning to use my programming language in some way. With what we know today, what I would do would be to make sure that that language ends up in browsers. Because the web, the internet and the web is here to stay, and so the language that comes with the browser will automatically take the winning one. It doesn't matter what the other languages are because they're not in the browsers, so they lose by default. The language that is in the browser wins. Okay? And that language step happened by historical accident using JavaScript. So, I'm Martha. I work at Element. I also do a lot of things with languages, with language design and language implementation. It's kind of a hobby in my spare time to deal with languages and so on. And so for me, JavaScript kind of looks like this. Am I ashamed to say? JavaScript looks like the grammar of the language. It probably takes a little bit of explanation. At the top here is an entire program. And at the bottom there you have the nitty-gritty parts, like individual words that you type in the language, like for loop, or bar for exploration and so on, or individual numbers and strings and so on. And they all come together. These are all, every circle here represents one kind of thing that you can write in JavaScript. And bigger things contain smaller things. Now this diagram that you're seeing represents what's now probably a fairly old version of JavaScript. So let me guess it must be 3 or something, which is several years old, now decades old. But still, it gives you a sort of grammarian view of the language approach. And I'm a language enthusiast, so I think of it this way. But that's not what we're going to do today. And I imagine people are eating a sigh of relief that not every slide will look like this. Because the history of languages is in the end about the people that were involved and the people that were influential in making that language come about in the first place, and then also evolve into what it is today. So it picked out 6 people. These are 6 people that were influential in pushing JavaScript in various ways. Actually, the first one is influential in creating it in the first place, under very, I would say, random and in retrospect, a little bit funny circumstances. The other side has been influential in sort of evolving the language and making it richer, or spreading it to the world, or making us all look at it in a different way. A little bit disappointing that these are all 6 men. There should have been women in this list as well. I'm sorry I cannot do anything about that, the influential people were not mixed among big influential languages. But we're going to have to sort of rewind back to the 90s when all this started. So we're going to jump into our time machine here and go all the way back to 1995. And that's when we meet the first person on the list, Brendan Eich. And Brendan Eich is, in 1995, a bit younger than in this photo, and sort of enthusiastic, already sort of experienced person who likes to write small languages and fix problems by implementing a language and making that language do the right thing. And so he starts at Netscape, which is fairly new startup at that point. Netscape is getting into the browser game. Actually, there are not many browsers at this point. There is Internet Explorer, and there's Netscape, and there are a few older ones, which some of us may remember. One of the influential ones is actually called Mosaic. Mosaic was the first one to have images, if you can imagine that. And the images were not part of HTML or anything. Mosaic just added them because, of course, you wanted to look at images in the browser. And so Netscape was a company that evolved out of the Mosaic effort, and they actually wanted to call their browser something like Mosaic Killer, but that wasn't really kosher to do so they abbreviated it to Mozilla, and then somewhere along the way they changed it to Netscape. And so the company was called something like Netscape Corporation, and the browser was called Netscape Navigator. Many people here actually use Netscape Navigator. For you as well as for me, it's very sort of way too fancy actually. I still remember fondly or not so fondly going into the composer, the editor that came with the later version of Netscape Navigator, and whenever you did anything with Netscape, it just crashed. So you got into a very good habit to save every 5 seconds. So that's Netscape Navigator. It was not a lot of fun and games though. It was the height of what we now call the first browser war. It was a war entirely without human hands. No one died in the browser war, but companies died. Eventually Netscape actually died, and what rose out of the ashes there was Mozilla Firefox. But then many years later, now there was just an intense battle between Netscape on the one hand and Internet Explorer on the other hand. For example, Netscape was free at that point, and Internet Explorer had to be bought for money, so one thing that Microsoft had to do from the very start was to make their browser free as well. They just simply didn't have any choice from a competition perspective. But Microsoft went one further and bundled their browser with the operating system, so now it was sort of stuck, or it was at least a default, and that was a move that they got into legal trouble for. They actually went into court because of antitrust. So there were very high stakes here. In fact, Microsoft at this point didn't really believe in the internet or the web very strongly in the middle of the 90s, but they saw that they had to give this effort and invest the money and people hours just not to miss the boat, miss the thing that was happening here. In this case though, in 1995, when Let's hired ICE. They were convinced that they needed something more than just the HTML from styling and so on. They needed some movement on a page. They needed some behavior. So HTML was meant to be this glue language for the web, something that made the web a little bit interactive, something that made it actually behaving like a solution, not just through the page. And you know, if we take a step back, why does JavaScript have this default? We'll come back to that topic, of course, but it's because JavaScript was meant for really, really small things. And if you are a newcomer and if you don't really care about declaring variables, then it's kind of cozy and convenient in this work to just name a variable that you have to think of. You don't have